Alright, we're looking at 8.6 and 8.7. The first thing we're going to talk about is indirect measurement using similar triangles. Indirect measurement means you're not going to take a ruler or tape measure straight to the thing and just measure it directly. So we have to find a measurement for it some other way. So we use our mathematics information, our knowledge, to measure it without a super long tape measure. For example, if you want to measure the height of a mountain, probably don't have a long enough tape measure to make that happen. So we got to do it some other way. So let's just go through some examples and see what this would look like. Alright, when Stephanie stands 2 feet from a lamppost, her shadow is 3 feet long. If Stephanie is 5 feet tall, how tall is the lamppost? Okay, so here's Stephanie. And she stands 2 feet from a lamppost. So this will be 2 feet. And here is the lamppost. Now the lamppost is putting off light, so just think about the light coming across here, and that creates the shadow right here. And the shadow is 3 feet long. Well, anytime we talk about the height of anything, it should be perpendicular to the base or perpendicular to the ground. So just imagine this. So you got a right triangle right here, and you got the bigger right triangle here. Alright, if Stephanie is 5 feet tall, how tall is the lamppost? Round to the nearest hundredth. Now, they don't say anything about similar triangles as you're reading the problem. However, both of these triangles, the big triangle and the little triangle, have right angles because height is perpendicular to the base. And because they're overlapping the way they are sharing this angle. So, if you remember the 3 ways of proving triangles are similar, one of them was angle-angle similarity. Well, we have 2 pairs of congruent angles. These triangles have to be similar. And if I know they're similar, what we learned about the sides of similar figures is that they are proportional. So I can set up a proportion to solve for x. So for the little triangle, the 2 sides I have for the little triangle are 3 and 5. I'm going to put them both in the numerators of the ratios. And then I want the corresponding parts from the larger triangle to be paired up with them in each ratio. So the 3 from the little triangle would correspond with 5 from the big triangle. This whole thing down here is the side length for the big triangle that corresponds with the 3. And then the 5, the height of Stephanie, corresponds with x, the height of the lamppost. So there's our proportion, and now all I have to do is cross multiply. If you know your shortcut for this type of simple proportion, you can do that. If I'm doing it the long way, I got 3 times x. 5 times 5 is 25. And when we cross multiply, we just set the cross products equal to each other, and then we solve the equation. So now x is being multiplied by 3, so I divide by 3. And the direction said to round to the nearest hundredth. So we get 8.333. The next 3 is not big enough to round up. So that lamppost is approximately 8.33 feet. Let's try another one. A tree casts a 36.5 foot long shadow. At the same time, a 28 foot flagpost, I can't read. A 28 foot flagpole casts a 14 foot long shadow. Find the height of the tree. Alright, so we got a tree. Amazing artwork there. And it casts a shadow that is 36.5 feet long. At the same time, a 28 foot flagpole. So here's our flagpole. Casts a 14 foot long shadow. Now that was a 28 foot flagpole, so this is 28 feet, and that's a 14 foot long shadow. Now the important part here is that it's at the same time, so that sun should be hitting them at basically the same angle. So that means that this angle of elevation should be the same for both of them. So here you have right triangles. The right angles are congruent. This angle is congruent. So by angle-angle similarity, these are similar triangles. Therefore, their sides are proportional. We want to find the height of the tree. So let's set up a proportion. Take the two sides from this triangle. I'm going to put those on the tops or in the numerators of each ratio, and then match up their corresponding parts. The height of the tree corresponds with the height of the flagpole. The shadow of the tree corresponds with the shadow of the flagpole. So there's the proportion. We cross, multiply, and solve. The shortcut would just be multiplying these two and dividing by 14 if you want to do it the shortcut way. If I'm doing it the longer way, it's 14 times x. And then we got 28 times 36.5 is 1,022. So I cross multiply. I set those cross products equal to each other. And then it's solving an equation. X is being multiplied by 14. So I divide by 14. We get 73. So that tree is going to be 73 feet tall. Alright, let's try one more. A mirror is on the ground 8 feet from Ricky and 19 feet from a flagpole. So here's Ricky. There's a mirror on the ground that is 8 feet from Ricky and 19 feet from a flagpole. Ricky can see the top of the pole in the mirror. So here's his line of sight looking down to the mirror, and that mirror, he's seeing the top of the flagpole. Now again, height is always perpendicular to the base, so I should have right angles here and here. And if you know how a mirror works, the light's going to come in and out of that mirror at the same angle. So those angles are going to be congruent. If Ricky is 6 feet tall, how tall is the flagpole? Alright, so just like on the previous problems, we have similar triangles because of angle-angle similarity. We got two pairs of congruent angles. Therefore, because I know the triangles are similar, I know their sides are proportional. So I'm going to take the two sides from this figure, put them in the numerators, and then match their corresponding parts up. So the height of Ricky is corresponding to the height of the flagpole, and the distance between Ricky and the mirror corresponds with the distance between the flagpole and the mirror. So there is the proportion. Cross multiply. X times 8 is 8x. 6 times 19 is 114. And then x is being multiplied by 8, so we divide by 8. 14.25 feet. Alright, let's talk about some other things we want to talk about today. We're going to talk about parallel lines and proportional segments. And there's a few different things that we're going to learn about that kind of create these types of situations. Proportions can be used to find the lengths of segments determined by parallel lines. The first thing we're going to talk about is the triangle proportionality theorem. If a line is parallel to one side of a triangle and intersects the other two sides in two distinct points, then it separates these sides into segments of proportional length. So here's an example. We got a triangle. Here is a line that is parallel to one side and intersects the other two sides. It's intersecting both of them. Then it separates the segments into, it separates those two sides it intersects into proportional segments. So line segment CB, the distance from C to B over the distance from B to A equals the distance from C to D over the distance from, from D to E. Alright, so distance from C to B over distance from B to A, distance from C to D over the distance from D to E. So we're going to see that type of proportional situation happen every time we got a line parallel to one side of a triangle intersecting the other two sides. So right here, here's a triangle. This line is parallel to one side, it's intersecting the other two sides. I can set up a proportion just following this pattern. X over 1 equals 8 over 2. And then we're just cross multiplying and solving. So 2 times x, 1 times 8. Cross multiplying sets up the equation, and then we just solve for x. Just solve the equation. Okay, let's try it again down here. Again, you have a triangle. Notice that this has been labeled parallel with one side of the triangle, and it's intersecting the other two sides, so it's going to split those sides up proportionally. So I set up the proportion. 5 plus x over 3 equals 8 plus x over 4. So then we cross multiply. Now when you cross multiply in this type of situation, you need to make sure that that 4 is multiplying times both the 5 and the x. You have to distribute that multiplication. And the same thing happens going the other direction. You got 3 that needs to multiply times 8 and times x. So again, you have to distribute the multiplication. So there's our equation after we've cross multiplied. And we just solve. Oops, that was 3 times x, so it should be 3x. We don't want x on both sides, so I'm going to subtract 3x to get rid of it on one side. And then I want x all by itself, so I'm going to subtract 20. Find out x is 4. Alright, another situation that creates proportional segments. If 3 or more parallel lines intersect 2 transversals, then they cut the transversals proportionally. So notice 3 parallel lines, you get 2 transversals. Those transversals are split into proportional segments. The distance from P to Q over the distance from Q to R equals the distance from D to E over the distance from E to F. So anytime you have this scenario, we set up a proportion to find missing segments or to solve for variables. So right here, find the value of x, round to the nearest hundredth. You notice the 3 parallel lines, the transversals. I can set up this proportion just following the pattern up here. 5 over 7, x over 9. So then we cross multiply. We got 7 times x, 5 times 9, and then solve the equation. Now it says round to the nearest hundredth, so 45 divided by 7, 6.428. 8 is big enough to round up, so 6.43. Okay, let's try one more. Same type of scenario. 1, 2, 3, 4 this time though, so a little more complicated. It said 3 or more parallel lines. We'll split those transversals up proportionally. This time we got 4 parallel lines. So let's say we want to solve for x. Then I want to make sure I'm not including any y's. So I'm just going to ignore that part of the picture for now. Here's 3 parallel lines. I can set those up proportionally to solve for x. X over 3 equals x plus 3 over 4. So there's a good proportion to solve for x. So let's cross multiply. I got 3 multiplying times x plus 3, so I have to distribute 3 times x, 3 times 3. Working the other direction, we have 4 times x, which is just 4x. So we set those cross products equal to each other, and then we solve. I don't want x on both sides, so I'm going to subtract 3x. That'll get rid of it on this side. And there's x. X is 9. Now we want to find out what y is. I can do this several different ways. But now that I know what x is, I know x is 9. I know that's 9. And 9 plus 3 is 12. So now that I know what those are, I can ignore this part of the picture, and we can set up a proportion to solve for y. So there's the 3 parallel lines, transversal. I know that y over 9 equals 2y minus 5 over 12. So then we cross multiply. 9 times 2y minus 5 is equal to 12 times y. Again, when we're multiplying 9 times 2y minus 5, we have to distribute. 9 times 2y is 18y, and 9 times negative 5 is a negative 45. Now, we don't want y on both sides of the equation, so I'm going to subtract 12y to get rid of it on one side. Now, that leaves me with nothing over here. Make sure you leave the 0. Okay, we're going to add 45 because we're trying to get y by itself. And then the last step, we got to divide by 6. So 45 divided by 6 is 7.5. Alright, last one. One more situation that sets up proportional parts here. If 3 or more parallel lines cut congruent segments on one transversal, then they cut congruent segments on every transversal. So this goes beyond just being proportional. These are going to be congruent. So it's similar to the last one. You got 3 or more parallel lines. If it cuts if it cuts one of the transversals into congruent segments, I know it'll cut any other transversal into congruent segments. So I know that x plus 1 and that 2x minus 5, those are going to be equal to each other. So I set them equal to each other because they're congruent, and then I just solve for x. And there it is.